Welcome everyone to a puzzling project by the Jokers. The Jokers team consists of Theo Beck, working on design documentation and the presentation, Ashley Andringa on design analysis and the presentation, Kayla Hackett on design, CAD, printing and documentation and assembly, Sydney McDonald on design, CAD and animation, printing and assembly, Andrew Jones on design, analysis and presentation, Shea Mielke on design, CAD, assembly, and presentation, and Joseph Christensen on design, documentation, and presentation.
Throughout this presentation, we will explain the project's purpose, the design goals and objectives we have established, and review the features of the final assembly. We will also highlight the lessons we learned and discuss the use of additive processes for our project.
The purpose for this project was to design a device that is easily printable, but also functions smoothly. We wanted to take advantage of the quote-unquote free complexity that additive manufacturing affords to us in this design. We also wanted to come up with a design that would not be easily manufactured using traditional processes. We wanted this to be an original and creative design that also integrated all requirements present in the project description for this class. Our initial thoughts on the design were to create a unique puzzle container for storing small valuables. The core concept for this container would be multiple puzzle elements and then an internal and an external rotating cylinder. The design goals for this project included maintaining low cost in accordance with our $50 limit, achieving high part and surface quality in relation to the printer used. We're hoping to achieve relatively fast print times and incorporate articulating components and embedded metal threads. We're also looking to maximize our ability to showcase additive manufacturing abilities through this design. The drawing on the left side of the slide shows some of our initial design ideas for this device. These included hinge articulation on the lid and a torsion spring to open that lid. We ended up going away from this idea as we wanted to reduce post-processing and assembly required. Our initial thought was also a normal box shape like the picture shown in the top right corner of this slide. However, we realized that this catered more towards traditional manufacturing processes, and we wanted to showcase the freedom of additive manufacturing as much as possible.
The puzzle box consists of 5 main components. The first being the outer body and the second being the inner body, denoted by the blue cylinder. The blue cylinder rotates relative to the outer body through the use of a clearance. The sloped edges on the top and bottom work to secure the inner body within the outer body. It was our goal to keep the parts nested as if they were one unit while still allowing them to move with respect to each other. Printing them together and using the slopes made this possible. The next main component is the internal metal thread, located at the bottom. This allows for a screw to be placed in the inner body. When the screw is in, the locking peg is nested in both the inner and outer body, preventing the two from rotating relative to one another. Once removed, turning the device allows the peg to slide into the long cavity in the inner body, allowing them to then rotate relative to one another. A special designed key is used to help better the rotation. Once the inner and outer bodies are aligned, the lid can easily slide off. The complex curvature and unique design of the lid highlights the benefits of using additive manufacturing. Even the embossed flower design that extrudes nicely from the outer body would have been more challenging to achieve with a traditional manufacturing method. Extra steps would have likely been needed here should that traditional method have been taken.
This animation in SOLIDWORKS shows the internal locking mechanism of the box. Starting in the open position, the lid slides on and the rod slides into the internal chamber. Once rotated 90 degrees by the key, the rim of the inner body locks the lid in place. The rod is shaken into a pocket in the outer body, locking rotation, and the screw keeps the rod in place. This process is reversed to unlock.
As was mentioned earlier, the project cost could not exceed the $50 maximum. This meant the team used materials which we already possessed or purchased inexpensive materials such as the PLA and PETG filaments we used. However, all material costs were still considered for the final material cost summary later, including those already in our possession. Because both filaments have a different percentage of shrinkage when cooled, the team wanted to make sure that we could accurately create the desired designs. Some concerns were that the angles would be too steep to accurately print and that the tolerances of the two different filaments would impede assembly after printing due to the different shrinkage percentages, especially where the lid met the body. This led to some prototyping of small print parts to test the form and shrinkage of the different components. One example can be seen in the upper middle right image. Once the team was certain that the designs could be reliably printed, we were able to move on to the actual production. The team wanted to make sure this puzzle was robust as it would possibly be used as a fun locking storage. However, we also wanted to minimize the print time overall. This led to the team using an infill of around 25%, which helped strike the balance between print time and product strength. For the surface finish of the part, the limiting factor was the nozzle side, which affected the road size and therefore the surface finish. As with many FDM parts, this finish is slightly ribbed throughout the surface of each part where the roads were printed. And although post-processing could have been done to create a smoother finish, the team decided against sanding or painting to keep the post-processing time and therefore the overall production time shorter. Here you can see the infills used as well as the finish of the lid, part 5.
All parts of the puzzle box were printed on the original Prusa i3 melt extrusion printer. To the left, you can see the printer settings used for the inner and outer body parts. That first printer setting you see is the 0.2 millimeter quality MK3. The 0.2 millimeters is the layer height. Now, we could have used 0.1 millimeters, but this would have doubled the time taken to print without providing much of an increase in resolution. Now, that quality aspect allows us to pick what we wanted to focus on. There are two choices. You can focus on speed or you can focus on quality. And of course, the team wanted to have a high quality part. Now, for the filament, you can see it says generic PET. The filament we actually used was PETG, but the settings for the temperatures, the head speed, and the fan speeds were all the same for both the PET and the PETG. Now that next setting you see is the support. And one of the great things about our design is that no support was needed at all for any printing. And that is because A, we designed it in a way that no support was needed, and B, because of the way we placed the components onto the printer. Now that last one you see is the infill, 25%. This is the most optimal infill we found after conducting various tests with samples in which we determined that it would not provide any sagging with the holes or provide any poor surface quality, while still giving it that good structure and being lightweight. Now, the nice thing about this program is at the bottom, it does show you how much filament is used. So we use 394.53 grams of filament for this one print. And that took us approximately 1 day, 15 hours, 10 minutes, and 26 seconds to print.
Once we had our final product completely designed and printed, we could examine its functionality. We incorporated many unique features into this device. The most interesting is the hidden internal components. The key proponents for opening this box are hidden inside, making it difficult to decode. This includes the square rod insert and the rotating inner cylinder. This brings us to our next feature, the inner and outer nested cylinders. These two cylinders that you can see were printed together, locking the inner within the outer cylinder. However, they can still rotate freely, which makes opening this box after unlocking easier. Again, the outer cylinder has a unique flower embossment, which helps showcase the additive advantages. Another showcase of additive advantages is our sophisticated lid design. The complex geometry here highlights the unique shapes and dimensions that can be accomplished in 3D printing. The best highlight is how well our parts integrated together. There are some larger gaps, but overall each component fit together and worked as desired to make a fully functioning puzzle box.
Specific dimensions were measured on each of the 5 components to determine the dimensional accuracy of the finished product. Parts 1 and 2 make up the body of the box, with Part 2 nesting completely inside the cylindrical interior of Part 1. On Part 1, the inner diameter of the cylinder was measured, and on Part 2, its outer diameter was measured. These measurements gave us the accuracy of the clearance fit between the parts that was needed for easy rotation. Part 3 is the bar that locks Part 1 and 2 together, stopping their rotation. The length of the bar was measured, as if it was too short, Part 2 could rotate freely inside of Part 1, even in the locked position. Part 4 is the key that's used to rotate Part 1 and 2, and it features 2 pins that fit into the holes in the base of Part 2. The diameter of these pins determines the quality of the fit into its corresponding holes. On Part 5, the width of the dovetail pin on its base was measured. This pin fits into a slot on Part 1, which ensures that the lid stays in place until the box is unlocked. The fit of this joint determines if the box can be opened before the unlocking sequence is completed. The values measured from the printed box were compared to the dimensions specified in the computer models used, and a percent error was calculated. Almost every measured dimension was within 1% of the desired value, except for the diameter of the pins on Part 4. While they had over a 2% error, they were only 1/10 of a millimeter off from the desired value, and the part functioned as designed.
For this additive manufacturing project, we worked with both PETG and PLA. Physical strength is typically higher in PETG, so this material was used for most of our critical components. PLA, on the other hand, doesn't string or ooze as frequently as PETG, so this was a better material choice to achieve a higher quality surface finish for the complex contours and overhangs of the lid. The screw and threaded insert were already fabricated when purchased. Steel was an ideal material for this because it could be heated up without melting or deforming, and it could reach a high enough temperature to reach the glass transition temperature of PETG. This allowed us to adhere the threaded insert to an existing hole in Part 2 easily.
This table shows the total costs incurred by the group for this project. We were able to maintain within our $50 budget for the project in accordance with guidance. We had enough filament to both print the final parts as well as all of our prototypes and samples leading up to that final print. Some cost reduction impacts included the use of PETG and PLA, which are relatively inexpensive materials. We also had a relatively small design, which reduced the material requirements for our device. We had no strength sacrifices in order to make use of this inexpensive material, and the size decision was driven by functionality, but it did have the side effect of reducing our costs. We did take advantage of the benefits of additive manufacturing to consolidate the printing of both the outer and inner body into one print, but this had no impact on costs thanks to the flexibility of additive manufacturing.
Many lessons were learned during this project, both during the design phase and the printing of the box. The dimensions needed for the interfaces between parts were difficult to predict as the accuracy of the printer was unknown, and the parts can shrink when the material cools. It was also difficult to predict how accurately the small details that were required would be printed while we were designing the parts. Printing times were also much longer than expected for the large parts of the box, and this made printing small test samples very useful. With these samples, we were able to test the fit of the threaded insert and did not have to reprint any large parts. We also learned during printing that the Z offset of the printer is critical for the print adhesion, and the large parts of the box required higher infill percentages to prevent distortion on the top of the part.
Additive manufacturing was an excellent choice for this device. First of all, additive manufacturing allowed for multiple iterations of the device to be made. For this device, there were 3 different iterations within the lifespan of the product. Additionally, additive manufacturing allowed for creative and unique designs that would be expensive or impossible with other methods of manufacturing. Additive manufacturing also provided a good finish for the intended purpose of the device at a low cost. Melt extrusion was used to create this device. This process offered an inexpensive method that also allowed for multiple rapid iterations throughout the design process. This device would have been difficult to make using any methods involving powder, including directed energy deposition or powder bed fusion. This is because the powder from these devices would be expensive to remove and would also inhibit smooth rotation between the two layers of the box. Photopolymerization could also be used for this part, but would be much more expensive. Additionally, with photopolymerization, a post-processing full cure may be hard to achieve between the two different layers of the device. Finally, melt extrusion was also chosen because the process was readily available and members of the team also had previous experience using this method.
A key benefit of additive manufacturing is the freedom and creativity that can be achieved in design. The nested articulating inner and outer cylinders of our project would have been impossible to manufacture in just 2 parts for any traditional manufacturing method. Likewise, the curved and contoured geometries of the lid and outer body were designed specifically with an additive process in mind and would be much more difficult to replicate with other processes. To utilize the capabilities of additive to its fullest extent, we limited overhangs to 45 degrees to eliminate the need for support material. This dramatically reduced the amount of post-processing necessary and increased the surface quality. One other key advantage of additive manufacturing is that we're able to create prototypes that isolated key components of our design to see if everything worked as expected. This made it apparent how easy it was to go back and change designs without retooling, lending to an amazing opportunity for customization in future designs.
Throughout this project, the team has learned a lot about how to design for additive manufacturing and the physical process of 3D printing. We were able to work together on a team of 7 to create a fully functioning puzzle box with hidden internal components, parts printed together, a metal threaded insert, and complex geometries. The knowledge gained during this process will help us in our future careers as engineers. Thank you.